Welcome back to Introduction to Statistics. In this video, we're going to be talking through the vocabulary of statistical data. The first lesson in many mathematics courses is tied to vocabulary, statistics a little bit more so than the usual math course. And that's why I'm resorting to a PowerPoint presentation for this video. Usually I prefer using my touchscreen as a blackboard and giving what we generally refer to as a chalk talk, standing in front of you, writing things on the board and working through problems. But in order to make sure that we're all speaking the same language, we start off with this dive into the vocabulary of statistics, and leaving it here as the first lesson. So as we go through the course, if there are things that you're not quite sure what we mean when we talk about them, you can go back and take another look. All right, let me get my head out of the way and let's just start going through this. I promise I'll give you a little bit more than just reading the information on the screen here. But we have here variable is a characteristic or attribute that can assume some different values. Data are the values that the variable can assume. A random variable is determined by random chance. When you have a collection of data, you have a data set. A datum or a data value is the singular. Data is the plural. The word variable should be something that you are familiar with from your previous study in mathematics courses. A variable is a measurement that can change value. When you've used it in the past, for example, the variables L and W in the formula for the area of a rectangle, area is A equals L times W. If you have a different rectangle, you measure a different L and a different W. It's the same idea here. A variable is a characteristic that can assume different values. When we're looking at this statistically, we're trying to look at things a little bit more generally. So instead of just saying, okay, we can look at this rectangle, we can determine the length and the width of the rectangle, and then we can move on from there. In statistics, we are surveying. We are surveying hundreds or thousands or millions of rectangles. We're looking at the length and the width of each one. So the data we are collecting is the measurement. And the variable we're collecting data on is the length of the rectangle. So we look at a rectangle, we measure its length, we record it, we set it aside, we look at a new rectangle, we measure its length, we record it, we set it aside, we continue onward. It's the same idea that you've used in the past talking about variables and the measurements that fill those variables, but extended out to something a little bit more generalized. And then I want to stress one more time here at the bottom, a data set is the collection of all of the data values. The word data is plural. Data is the collection of all of the measurements we took for all of the rectangles. A datum, a singular data value, is the measurement that we took of the length of one particular rectangle. When we are looking at collecting our data, we have to find a way of doing so. We can look at the entire population. Thinking about my silly analogy of rectangles, the population of rectangles is every rectangle that has ever been drawn or formed ever in the history of the universe. If we could collect data on literally every single rectangle that exists, then we would have a census of the rectangles, data on the entirety of all of them. But since that's not possible, we turn to a sample. We take a small subset of the population of all of the rectangles, and we use that as our tool. And when it comes to creating samples, we do have to be careful. In order to do meaningful statistics, we need to have a representative sample, a properly selected sample, so that we know that our sample will have the same or close enough to the same characteristics as the entire population. A biased sample does not have that. We're getting to the point that my analogy to rectangles is getting a little bit out of hand. So let's turn to something that sounds a little bit more population-based and collect data on the heights of people. Now, I am 6 feet 2 inches tall. So if we're looking at the population of all of the people in the world, there is one data point, one data value, my height. Once again, I can't collect the height of literally every person who has ever existed. That's just not feasible. It's not possible. And so I need to create a representative sample of population. I need to select people at random. Now, depending on what I'm trying to do, I might choose to exclude some people. For example, if I'm trying to do a statistical analysis on adult men, then I want to only select people who have finished growing and are male. If I select a 12-year-old girl as part of the sample of adult men, that is something that is problematic. I also have to make sure that my sample is representative. I need to make sure that I am selecting a very average looking sample. Find some way of predicting how many taller or shorter people and try to find a way to match my sample to that. If I choose a sample of the heights of adult men and I choose only professional horse jockeys, professional horse jockeys are chosen in very large part for the fact that they are very small and light in weight, so they give less resistance to the horse, less effort for the horse to carry them. That's going to give me a biased sample. The average professional horse jockey is much shorter than the average adult male. On the other extreme, if I choose a sample that is entirely professional basketball players, the average professional basketball player, I think we can all agree, is taller than the average adult male. And so we have to make sure not to bias our sample by choosing some subset in a way that favors an extreme of the data set. Now that we have our collection of data, we have to think about what we want to do with them. In the first part of this course, we're going to be looking at descriptive statistics. We're going to be looking at tools that we can use to talk about what the data set looks like. Many of these tools are things that you've run across in the past. The idea of the average, formerly the arithmetic mean, is the average you probably are most familiar with, although there are others. The median, the mode, the geometric mean, the midpoint, and certainly others that I'm not thinking of off the top of my head. Those are some of the tools of descriptive statistics. They try to give you an overview of what the data set looks like. The other tool that we have in statistics is the idea of inferential statistics. We take a population, or more generally, a sample of a population. We look at what is happening with that population or the sample, and we use that information to predict what is going to happen in the future. Sometimes it's a matter of a timeline. If we collect data on the earnings of a particular business month after month, year after year, we might try to make a prediction of how much that business is going to earn next month and next year. The most common inferential statistics, the most important ones for this course, are hypothesis testing. And we're going to spend the last half of the semester talking almost exclusively about hypothesis testing. We use hypothesis testing to evaluate claims. A common idea in hypothesis testing is to take two samples of a population, assign one of those samples as the control group, and have them continue on as they are. Assign the other of those two samples as the experimental group and have them try something different, a new medicine that is claimed to treat the illness that everyone in these two samples has, or a new instructional technique that is claimed to be a better learning tool for these groups of students, or any other idea that we might want to test. We look at that, we collect statistical information, we go through one of the analyses, and again, we're going to spend the last half of the semester, literally the last 5 of the 11 lessons in this course, are going through 5 different hypothesis tests. So we'll have a couple of different things to choose from, and we'll try to use that to make a prediction as to whether our experimental procedure is better, worse, or no different than just doing nothing. Kind of taking a step backwards, now that we're talking about we have data, we have a population, we want to sample that population, we want to do hypothesis testing, we need to figure out how to find a sample that is representative. And there are a couple of different tools that are commonly used in sampling: random samples, systemic samples, cluster samples, stratified samples, and then kind of mixed sampling techniques that combine some of these. Each one has its pros and cons. Random sampling, I think, is the classic idea, drawing names from a hat or using a random number generator. Every single member of the population has an equal chance of being selected. The advantage of random sampling is that the statistician has absolutely no input on what the sample looks like. The disadvantage is that it's often very challenging. When you choose a random sample, you need to think about how large of a sample you need to make things representative, and that tends to be a relatively large number. So, for example, if I'm trying to find a sample to represent the world population in order to test a skincare technique, well, if my sampling technique is random, then that means that I'm going to select a person living in Chicago, a person living in Los Angeles, a person living in a small village in northern Canada, a person who is currently part of an uncontacted tribe somewhere in the Amazon rainforest, and so on. It's not a very practical sample when you're looking at something that large. And so we generally are going to need some tool to make our representation work and still be practical for the researcher. Uh, Systematic sampling kind of falls into the same idea. Um, you probably have dealt with systematic sampling in some point in your education. where the students in the class line up and file through the door, and you are handed in turn a red, a green, or a blue card and sent off to one of three different groups in order to do something. And as you come into the room, you are spread apart using that tool. Systematic sampling is very common in manufacturing, right? If you have an assembly line and you want to test 1% of the objects that come off of the assembly line, the thingamabobs in this slide, well, we will literally do that. We will collect a thingamabob, we'll let 99 more go through, we'll collect another thingamabob, we'll let 99 more go through, and we can be sure that 1 out of every 100, 1%, have been sampled. It's not random, we know exactly which ones are going to be sampled, it's determined, but if you have no control over how people are coming in or how objects are coming in, it's still randomized, right? If you have chosen that you're going to take the students filing through the door and take every fifth student, well, whoever lined the students up didn't know that, so they don't know what's coming and they can't make predictions. Likewise, if you've decided that you're going to take every 100th thingamabob off of the assembly line, but you have not communicated that to anyone who is working on the assembly line, then there's no way for them to make predictions about which one is going to come off. And you don't have to worry about things like somebody trying to cheat the system by making sure that they do one perfect and then race through 99 and then do one perfect and then race through 99 because they don't know that that's how you're sampling. Right. Cluster sampling is a sampling of convenience. We say here divide the population into clusters, but generally the population comes pre-divided into clusters. For example, if I want to survey students who are taking college writing, a very convenient way for me to get a sample of students is to choose one class section. I will choose the students who are taking college writing at 10 a.m. And those students are my sample. It's very convenient, it's very useful as a way of creating a sample because I can do it without having to think about it. I don't have to chase people down. I just know that I go into the 10 o'clock class whenever I want data. Generally speaking, there are a lot of ways that choosing a class section like this is going to give you a very representative sample. There's probably not much difference between the students who decide to take a class on Monday, Wednesday versus the students who decide to take a class Tuesday, Thursday. There might be a difference between students who want to take a class in the morning versus students who want to take a class in the evening. There might not be. So you have to think about what kinds of differences might show up with this kind of sampling, but a lot of the ideas should be the same. They're receiving the same instruction. They probably have a very similar background. They might have a different work ethic, but it should work as a representative sample for a lot of different cases. And then the last tool is stratified sampling. Stratified sampling is useful when the researcher already knows some things about the population. So for example here, if I want to survey students on their opinions of a class, and I want to make sure that I control for letter grades, which is something that tends to be difficult, then I might be able to stratify the group and then go from there. Something that I know very well as the one of the few mathematicians employed at the college, I very often get involved in statistical research. One thing that you see frequently in college courses is a student opinion survey. where near the end of the semester, we send out a request for feedback from students. One of the things that we know is that if we send out a feedback request near the end of the semester, and we do so in person in an in-person class, we are going to get a biased sample that is going to be predominantly A, B, and C students, because students who earn Ds and Fs have a tendency to not show up for class. On the other hand, if we try to do student opinion surveys by sending out a mass email, students who earn Ds and Fs are overrepresented in the responses, because very frequently a student who earns a D or an F in the course blames their instructor for that. Sometimes it's legitimate, sometimes it's not, but they are generally more interested in talking about that than students who are satisfied with the course. That's also something that's very important in modern society with social media. It has been shown frequently through studies that the number I've seen is different 5 times, 8 times, 12 times I've seen in different studies, but there is a significantly larger portion of people who are dissatisfied or disagree with a comment, a post, or a video who respond to it, compared to people who are satisfied with it, who are happy with it, or who agree with it. So if you post something on a social media platform, you are more likely to see responses of people who dislike your work than you are to see responses of people who like your work, even if there are far more people who like the work than who dislike it. And so we have to find ways of accounting for that. In the example that I'm more familiar with here, that I'm standing in front of, if I know the portion of students who earn an A, the portion of students who earn a B, and so on, which I can get pretty readily, the statistical analysis of what percentage of students in a course earn an A, B, C, D, or F is a really easy statistic to calculate, and we tabulate that regularly for our classes. Knowing that, I can ask that an email be sent to all of the students who earned an A in the class, asking for feedback. I can look at a group of the students who earned a B in the class and ask them for feedback, C's, D's, and F's. And I can probably not get a complete representation of all students, but I can select representatively in proportion to how large they are in the entire population. This is certainly the most difficult of the sampling techniques. It takes a lot of work in order to get this to work, and it takes a lot of foreknowledge. You need to know what kinds of things are going to potentially bias the sample, and you have to think about, or you have to know how common each of those things is in the population in order to try to account for that. It's a very valuable tool, but it is something that requires careful thought and consideration. Oops, there's the button I wanted. All right. Now, because a sample can be biased if we are not carefully, excuse me, sampling can be biased if we are not careful in how we choose our sample, that can result in what's known as sampling error. Right. This is something I'm going to stress throughout the semester. The idea of error for a lot of students calls to mind the researcher did something to make a mistake. That is not the case, right? Sampling error does not mean that somebody made a mistake in how they collected the data. Sampling error means that the sample that was selected to represent the population is actually a biased sample. The way that the sample was chosen is a mistake. The way that the data collected is not the mistake in sampling error. Human error is an issue that should always be corrected. There is no excuse to do research and get to the point of doing statistical analysis if there is human error involved. If you have a possibility that the person who collected the data made a mistake in collecting the data, the recourse is to throw that data out and collect new data. Excuse me. There is no such thing as a perfect sample or a perfect representative sample. Every sample is biased in some ways. A lot of that is in the fact that extremes, outliers of the data, are rare, and so they are always underrepresented. Consider, for example, the idea of trying to collect data on people's heights. That's one of the ones we've talked about before. I am, as I said, 6 foot 2 inches tall. As adult males go, that's relatively tall, but not uncommon. It's like 2% or so of the population of adult males is 6 foot 2 inches tall, somewhere in the 1 to 2%. So if I'm collecting data and I'm collecting a sample of 100 people, I should expect there's going to be 1 or 2 people who are 6 foot 2 inches tall in that sample. Being 7 foot 8 inches tall is incredibly rare. It happens. There are a couple of adult males who are 7 foot 8 inches tall, but it is a tiny fraction of a percent. And so if you are collecting and you're getting 100 people to represent the population, chances are you're not going to have anyone who is 7 foot 8 inches tall. That fact is a bias on the sample. For a lot of purposes, we're going to have biases like that, emissions on the high end, also emissions on the low end. It's incredibly rare to find an adult male who is 3 foot 2 inches tall. And sometimes those balance out, sometimes they don't. It's something that is difficult to control for when you are sampling, and it can produce an error in the result, a bias in the result. That's what we're talking about when we say there is a sampling error. A non-sampling error is a difference that occurs because the sample was biased. All right, so sampling error, again, not representative is biased, but showing a clear bias, showing um, this goes back to my, oh, I apologize. I said in an earlier video, I'm still recovering from a cold and my throat generally hates me right now. I apologize that I keep coughing. I try to mute the mic whenever I'm going to, but I can't always. Anyway, sampling error is a bias that is a statistical anomaly. Things like because there are outliers that don't occur frequently enough to show up in the sample, you have a problem. Non-sampling error is the bias like the samples I mentioned when we first started talking about heights. If I sample only horse jockeys, I am going to have a very biased sample. That is non-sampling error. I didn't choose a good way of sampling, and because of that, I have an error. Or if the other extreme, if I choose to sample only professional basketball players. All right, now that we have these tools, we can start talking about experimental design. I don't want to worry too much about these ideas because unfortunately, the reality is that this course is too short and we don't have enough time to design an experiment ourselves. But I did want to mention that experiments come in two general flavors: the observational study, where we just look at what's happening, or the experimental study, where we have a control group and a treatment group or an experimental group and try to compare what's happening with them. Um, when you are looking at an experimental study, you're going to have an independent and a dependent variable. You've heard those terms before in a basic mathematics course. When you're looking at a graph, y equals f of x, we say that x is the independent variable because we can choose whatever we want, and y is the dependent variable because once we choose a value of x, the value of y is determined. The same idea here. We're looking at choosing people. We can freely choose a member of the population to be part of our sample. We cannot freely choose what the measured data of that person is going to be. A confounding variable, something that we do not control for, going back to my example of letter grades. If I don't control for the letter grades that people have, I might get only students who earned an A or a B responding to my survey. I might get only students who earned a D or an F responding to my survey. And the opinions of students who get an A or a B are generally different from the students who get a D or an F in a particular course. All right. That takes us to a couple of discussion questions. In a nation as large as the United States, it's difficult to select a representative sample of the population. Political opinion surveyors put a lot of thought into stratifying the population in order to ensure that their samples are actually representative of the population of the whole. Do you know anything about this process? Have you read results of political opinion surveys or meta-analysis, people talking about how political opinion surveys are run? If so, share your thoughts. If not, I want you to think about what kinds of quantities you might want to control for. What kinds of things do you want to know about the population that you're sampling to make sure that your sample meets the same proportions as the population? How easy or hard would it be to actually get that information and control your sample? There's no real right answer. Figuring out how to make political opinion surveys is really a challenging task. But think about what kinds of things might be helpful. And if you want to talk about that in our discussion forums, that's a great place to go next. In any event, that's all I have for you here. So I'll wrap up with that, and I'll see you next time.